Hi, so thank you for joining us for the second lecture video for chapter one, which we've said that most of this, or maybe even all of it, is going to be the review of general chemistry materials. And last time I think we talked about mostly atomic orbitals, molecular orbitals, hybridized atomic orbitals that make up organic compounds and or really compounds in general and stuff like that. And in this second video, we want to focus on things like drawing Lewis structures, resonance structures. That's going to be a major thing. In addition, we want to pay attention to things like how we draw molecules in organic chemistry. So without further ado, maybe I think we've said this in class or in one of the lecture videos already, but organic chemistry is what drives biology. You could say biology is just organic chemistry at larger, or you could even say microscopic scale, but larger scale in the sense that a lot of organic reactions are all happening at the same time to all these different sometimes macro organic molecules. Anyway, so it's not surprising that basically most of the drugs that we use for medicine, right, those are molecules that elicit some sort of a biological response, right? Are organic molecules, and epinephrine is no difference, right? You might know where you might find these compounds. You might find it in an EpiPen if you are prone to having some sort of dangerous allergic reactions. That you're encouraged to carry one of these so that when something you are exposed to severe allergen, you could administer epinephrine quickly to prevent anaphylactic shock. But it happens to have this structure, and this is the most typical way we would represent the structure of epinephrine, the way we drew it. And I just want you to be thinking about this. It's this very specific, particular 3D arrangement of carbons, hydrogens, oxygens, and nitrogen that provides this medicine. If you arrange these four elements in any other way, you cannot expect to see the same or even a similar effect at all. And epinephrine has to have this exact structure from these elements. Based on the way we're used to seeing the structures in general chemistry, we might draw the structure like this, right? Each atom is explicitly drawn, or the elemental symbol, and all the bonds are shown, right? And one thing to note in this structure is some bonds, you notice, are lines, and then some are wedges and hashes. So let's discuss the details first. So the line structures, or line bonds, like this right here, right, that is understood to be in the plane of the screen or the paper, if you want to go old school, right? So all this ring and all these OH bonds, at least the way it's drawn right now, it's understood to be in the same plane. Same with this rest of the chain here. But when it comes to this wedge bond, that is understood to be out of the plane, as in pointing towards you. Okay, and then the hash bond, you see that here, as well as this hydrogen. Those are understood to be pointing away from you, sort of into the paper or the screen. Okay, and now, of course, that drawing is kind of cumbersome, and it might give you some sort of a headache just looking at it, just because it's so busy. If we omit drawing the CH bonds, just to condense it, right? Like maybe we could condense it like this, but this still looks fairly busy. So in our class, or organic chemistry in general, or in really in science in general, we would draw the structure in a format that looks like this, in the line drawing format. Okay. And this might be kind of a leap, but what we have done is we replaced each, because organic molecules have so many carbons, it's kind of cumbersome to draw C every time you see carbon atom. And so for that reason, we basically replaced all carbon atom with a corner, or another way to think about it is the end of a line is a carbon. So this, there's a carbon here, just like there's a carbon there, and so forth. Now, even this is a little bit busier than it needs to be, so often we omit all the heteroatom the hydrogen bonds, so that like you could, instead of draw NH, instead of just N bonded to H and so forth. So this is probably the most likely way that we would depict this structure. Okay, and again, structure is important in organic chemistry because that's sort of what determines bioactivity when you advance to maybe like biochemistry or medicinal chemistry or something like that. Now, in thinking about organic compounds, right, in organic chemistry, we like we said, it's the study of carbon compounds, so you can always see carbons, but the most abundant elements that you would encounter besides carbon would be hydrogen, nitrogen, oxygen, and also sometimes halides. Now we'll see some examples of sulfur compounds as well, but HNO that pretty much make up the majority, and halides, especially for the this semester. And I hope that in drawing all these structures, right, like what's on this slide, hopefully it becomes like second nature to you, that with some exceptions that we'll look at, each element almost always forms the specific number of bonds. And that has to do with sort of the number of valence electrons that they carry normally, right? Because outside these sort of normal number of bonds, carbons for 4, nitrogens 3, oxygens 2, hydrogens and halogens 1, they would have a charge, and charge is kind of a uncomfortable thing for an atom to have, right? Because that means you either have way too many electrons or way too few electrons. That's not sort of natural, or I should say, like, it's just high energy state. And so for that reason, these elements tend to have these same number of bonds. Okay, and this is a really important table to really be familiar with. But that comes really from the fact that if you look at the periodic table, you should be able to predict the number of valence electrons. Those are the electrons in the outermost shell of an atom, right? Because these are the number of valence electrons. I hope it makes sense to you that you need to have this red number of bonds to complete the octet rule, right? If you only have 4 electrons, each of those could bond with another atom that wants to share an electron each, and you can have 4 bonds to have 8 electrons total. And similarly, if you have 5, you need to have 3 other bonds, right? 3 other atoms that bring to the table 3 electrons to form octet and so forth, right? So these are the number of covalent bonds that are expected. Which bring us to the shape of the molecules, because once you have so many bonds around an atom, they're gonna have some sort of a 3D shape, because remember, molecules are really real thing, right? Like real things that exist, of course, have a 3D shape to them, because they exist in our actual 3D space, not just some stuff you learn about on a piece of paper or on the screen, right? They're actual 3D objects. So the shape of the molecules, how is it controlled? Because as we kind of hinted at with the structure of epinephrine, the shape of the molecule is all that determines the bioactivity of a molecule. And also the shape of the molecule is really what determines chemical reactivity, which is the main thing that we're going to study throughout the whole year of organic chemistry. So how is it determined? It's controlled by the valence electron repulsion. You might remember hearing this phrase, Vesper theory, or valence shell electron pair repulsion theory in general chemistry. Right. Hopefully, we don't necessarily have time to go over every part of this Vesper theory table, but if this looks kind of foreign, or if you feel uncomfortable with this, you might want to spend some time reviewing Vesper theory material from general chemistry. And one good thing to review that it's going to constantly come up in organic chemistry is when you look at a structure, can you figure out the hybridization of that atom? Okay, so if you have a linear molecular shape, because it only has two atoms attached to it, what would be the hybridization? Hopefully you can figure out that that's got sp hybridization, because you hybridize two atomic orbitals to make two hybridized orbitals, so you could bond with two other atoms, right? So you mixed one of S and one of P. And then if you need to bond to three things, you could have an sp2 hybridized orbital. Likewise, for four things, or four things that you have to bond to, you could have sp3, right? And if you need to be bonded to five things, and when we say things in this, vaguely say things in this context, we also mean non-bonding pairs of electrons, or lone pairs counted, right? So like one of the five could be a lone pair, or two of the five could be a lone pair, or even three of the five could be lone pairs. But it still has five things around it. And when you do, you have to have sp3 is not going to be enough, so you need to add another d orbital, sp3d, and likewise for one more sp3d2, right? That was Vesper theory and hybridization for you. And a lot of that can be gleaned from the structure that you draw, but that presupposes that you actually draw the structure correctly, and that is a most essential skill that you have to have coming from Gen Chem into OChem, because we're going to have to assume that you still have this skill, and that you completely understand how loose structure is put together, including things like formal charges. Hopefully you remember that, as well as resonance forms, because those things together describe the actual molecular structure and its property. So loose structures, like how do you draw them? Remember, these are the sort of drawing procedures, right? First you have to figure out the number of valence electrons. You could figure that out from the group number in the periodic table, and then you start drawing stuff, drawing some structure on paper, and then you subtract the electrons that you've used to draw the last step, whether it's bonds or lone pairs, right? So you subtract electrons as you go, and that's why you need to know the number of valence electrons total. And keep in mind the charge attached to the formula, right? Like if we're talking about this carbonate ion, CO3 2-, you add up the number of electrons for carbon and 3 oxygens, and you have to add 2 electrons because there's 2 negative charges there, right? Because that means you have 2 extra electrons, because the electrons are negatively charged. Now, and then you need to start drawing the actual structure. You need to know what the central atom is, so you have to determine that. Luckily for formula, a simple formula like carbonate, right? These simple either polyatomic ions or compounds, the first element usually is the central atom, so that's easy enough. Usually the least electronegative atom forms the central atom. And that's a pretty good general rule. And of course, hydrogen cannot form the central atom because it cannot be bonded to a bunch of things. Carbon can, which is the reason why organic chemistry exists, because carbon can bond to many different things, and it can form 4 bonds, which is a lot, right? So that's why there's a lot of organic compounds, and so, hence we have a separate discipline we call organic chemistry outside of the inorganic chemistry, because inorganic chemistry is about all the other compounds. Organic chemistry is about carbon compounds. So, and then once you put down the central atom, you connect all the rest of the surrounding atoms to the central atom, and then you figure out how many bonds or how many electrons you've used there, and the leftovers will be placed on this molecule as lone pairs. And the most important rule here is that you have to remember to put the lone pairs on the outside first, and hopefully that makes sense to you, because remember the central atom is usually the least negative atom, electronegative atom. So the central atom should not take the lone pairs first. It should be the outside surrounding atoms that get the lone pairs of electrons first, because they're more electronegative. And then you check the octet, and then if it doesn't meet the octet, then you have to add multiple bonds, right? So that's sort of the procedure here. And for carbonate, hopefully without me going through it here, you can actually do that on your own. Hopefully you remember enough Gen Chem. Although I think during the class time we'll do some practice together, but I just want you to sort of refresh your memory about these procedures. Now, once you are able to draw the structure of carbonate, you might have drawn this structure A or this structure B with the double bond pointing to the right, or you might have put it pointing to the left, and the reality is all of these actually are correct, like 100% correct, right? Because it doesn't, and the reason why all these 3 structures are equally correct is because these are equal resonance forms of one another, right? And that happens when more than one Lewis structure that meets the octet are actually possible. Well, I should say some of the resonance structures don't necessarily have to meet the octet, like we'll see some examples, but so maybe we should rewrite this to say if several Lewis structures are plausible, then you would probably have a resonance. And another way to think about it is whenever you have a pi bond, or when you could have a pi bond, remember a double bond is formed with a sigma bond, and the second bond is a pi bond, right? Whenever you have a pi bond involved, you likely have resonance forms. And remember that actual molecular structure is the superposition or the hybrid of all the resonance forms, right? And in reality, it's not so much that electrons move from this oxygen to that, and then from that oxygen to that oxygen, and go around in a circle. You could picture it that way, but the reality is that there's all these negative charges are equally shared among 3 oxygens kind of at the same time. So that actual picture of carbonate is that you've got sort of a 2/3 of a negative charge on each oxygen. But that's kind of cumbersome to write or draw, and so we tend to we just pick and choose one of the resonance forms and draw that as the Lewis structure. But I just want you to know that the complete picture of this molecule or ion is the combination of these 3 resonance forms. even know if this is like a great analogy for you, but it's kind of like if you're familiar with like a theological doctrine called Trinity in Christianity. It's kind of like that. The Son, the Father, and the Holy Spirit are one God together. But and when you're just looking at one of those three persons, you're just kind of looking at a limited picture of the Godhead. That's kind of a similar concept to this idea of resonance. Okay, and hopefully that's helpful. And especially given that in carbonate structure, case all forms are equivalent. There's no difference between these three. In fact, if you look at the actual electropotential map of carbonate, like we said, the charge on the three oxygens seem equal among the three. Okay, so the electron map kind of looks like this. It's a symmetrical molecular shape. And it's because it's resonance. The electrons are in resonance. Another way to say that is that the electrons are delocalized, especially the pi electrons are delocalized to give us that resonance. Excuse me. Now, sometimes some of the resonance forms are not equal, which means like one resonance form is preferred over the other, and we would call that the major resonance contributor. And what we mean by that is the actual structure of this nitrogen, this NO cation that we are looking at is the hybrid of these two, but the major contributor contributes to the actual picture of this molecule more or better than the minor resonance contributor. Okay, so that's that something like that can happen here, and I want you to remember these 4 rules to judge which resonance form is more important than the others, or which resonance form represents the more predominant structure of this molecule or not. The first and most important rule is the octet rule, and as you can imagine, that's always the goal of any atom, right? Like this universe sort of exists to meet the octet rule, right? That explains all chemistry in some ways, right? Like biology is all explained by chemistry, or I should say biology is explained by chemistry, and so everything is explained by wanting to meet the octet rule, right? So it's most important. So between these two, it's actually pretty easy to determine which is major, because in the left structure, if you count the number of electrons for each atom possesses 8 electrons each. This nitrogen has 2 lone pair electrons and 3 bonds, which each bond has 2 electrons in it. So it's got 8 electrons around it, and same with the oxygen. So they all meet the octet. But this nitrogen here only has 6 electrons, or it's meeting this. It's a sextet state. So it's the minor contributor. Similarly, with this formaldehyde structure, right, you could potentially draw these 2 different Lewis structures, but what you notice is the right structure is not meeting the octet, and so for that reason, the left is the major contributor. Okay. The second most important rule would be to look at the consider the electronegativity of atoms. And then what we mean by that is if you have to have a charge, it's better to put that charge on the atom that has the most favorable electronegativity. So for instance, if you look at this enolate ion or anion, you could draw these 2 very legitimate Lewis structures. The left one with the oxygen being negative, or the right one with the anion or the negative charge being on the carbon here, right? Those are both equally valid, and what we notice is that one of these is actually better than the other, and if if you have to have a negative charge, it's better that it's on the oxygen, which is more electronegative, than the carbon, which is less electronegative, because electronegative atoms are happier to have that negative charge. Okay, so you want to put the negative charge on a more electronegative element. Likewise, if you have a cation, positive charge should be on less electronegative atom. So by that token, by that rule, right, you might think that between these two structures, the one on the right might be preferred because the positive charge is on nitrogen, which is less electronegative than oxygen. However, remember, rule number 1 is a more important rule. The octet is more important than electronegativity, and so for that reason, this is still the major. The third rule would be the charge separation, or you consider the charge separation and you make it minimal. Okay, so how do you do that? Well, you do that by you pick the structure that has like less or maybe no charge separations at all. You could draw both of these Lewis structures as valid Lewis structure for this formic acid. By the way, one thing I forgot to mention, when you go from this structure to that structure, when you go from one resonance to the other, the only thing that sort of seems to have moved around should be electrons and not bonds. Or the connectivity. If the connectivity of the molecule changes, or if the atom moves around, that is no longer a resonance form. It's a result of a chemical reaction. But if it's the only thing that moved are the electrons, and the connectivity is intact and the same, that's resonance, right? So going from the left to the right, you could say that that's the result of these lone pair electrons moving around. Okay, that's one way you can depict going from one resonance to the other, where you could say this lone pair is now shared between the carbon and oxygen, and these pi bond electrons are now exclusively on the oxygen as a new lone pair. That's what that is depicting. And in our class, if you didn't practice this in Gen Chem, in OChem, drawing these arrows to indicate the movement of electrons is the most crucial skill. So I want you to start practicing that, and when you draw resonance forms. Anyway, between the two, the left structure has no charge separation, but the right does. So it's better to consider this as a major contributor. Now, between these two resonance forms of carbon monoxide, which do you think might be the better or major contributor? Well, between these two, you might think the right one is the major contributor because it has less charge separation, but remember, rule number 1 is the most important rule, which is the octet, and so for that reason the left structure is the major contributor. So in summary, right, these are the 4 rules for resonance, or I should say judging resonance forms. I want you to definitely know this by heart, okay, as you draw different structures. And that would be the end of the second video.